We're Team 976 with SI Solar. We're making a sun tracking device. My name is James Barnes. I'm an electrical engineer. I worked on the optics testing. This is Jeremy Cheney. He's an electrical engineer, worked on PCB design. This is Jeff Patton, electrical engineer, also worked on optics testing. Then we have Joey Holroyd. He worked on the frame design. He's an electrical engineer. Then we have Tony Lay. He's a computer engineer. He worked on the microcontroller. And then finally we have Woo-Sung Jung, who's also an electrical engineer, and he worked on the motor selection. So basically the background of our device is we know that in the solar panel industry, people know that there are optimal fixed positions for solar panels depending on where you are on the earth. And what we know is that if you're tracking the solar panel with the sun, you could get up to a 60% increase in power outage with the solar panels. That's our goal here, is to increase power outage compared to solar fixed positions. Our objective for our device is to track within 18 degrees of deviation between where the sun is in rotation and tilt, as well as get at least a 40% increase in power outage with our device. And we want to make our device portable, easy to use, and expandable to solar arrays.
So given the spherical symmetry of the sun moving throughout the sky, we decided to take a spherical approach with our PCB design. We're actually going to have a two-part system. First part would be our solar angle detector, which consists of a PCB. Second part would be our solar panel orienter, which Jeff will talk about later. So the solar angle detector will have 280 LEDs on board. They'll create a net, and every intersection on that net would be two LEDs close together. We'll call those the nodes. So the circular prototype board you see there, as you get further from the center, you'll have different tilts associated with those nodes, and as you go around the PCB, you'll have different rotations associated with them. We chose LEDs due to the photodiode properties, so when you shine light on them, they will create a current. And we chose green LEDs specifically because the sun's light spectrum is centered at green. Whenever we design our circuit, we have our PCBs in parallel so that forward current from one LED will not go through the other LEDs, but rather straight to a load due to the reverse biasing properties of LEDs. On board, we'll have an accelerometer so we can normalize our output with respect to true level, so we can drive multiple of these solar orienters with just one angle detector. In our testing, we've detected a 400 millivolt difference between sunlight and darkness across a 1 mega ohm resistor. And we also plan to have a 2 centimeter hole for light to pass through onto the PCB, so we ensure at least one node is hit by light at all times.
For the frame, we have designed a 2-axis mount. With the 2-axis mount, we will have 2 motors. One motor to control the tilt of the solar panel, while another motor on the base to control the actual movement of the whole design. With that, we do understand that there is some issues, especially here in North Texas, with wind becoming an issue. We don't want this thing to turn into a windmill when it's supposed to be detecting, the sun, or not detecting, but pointing at the sun. With that, we have looked at worm gears and planetary gear sets. This will give us a mechanical advantage against the wind. Another issue as well is that this will be outside all the time. So we would also we also have to make it to where we're not having water get inside the system. With that, we are using a junction box for our microcontroller and our motor to be held in at the very bottom of the actual mount. And because of that, we're going to use that as the actual base of the whole system. Again, we are SI Solar. Special thanks to Dr. Neil Skinner. He was our advisor for this. If you have any questions, feel free to ask.
So you're differentiated, you just follow the sun, that's it, right? I mean, there are existing solar panels out there, right?
Yeah. That's not the main point of this. This is just to be used with a solar panel in terms of for our project.
I guess I would think the same thing. You guys have looked at all, like say, standard panels or typical panels. You guys are able to utilize or mount, support, rotate, angle with all the existing products right now, right?
Yes.
Okay, you said, so is cost effectiveness going to be part of this deal?
Yeah, so in total, we want to make this under $500. Right now, that's using off-the-shelf products, so manufacturing would be a lot cheaper as well. The main benefit over standard systems, so these use a GPS for the most part, whereas this would be completely self-contained. It would just be everything that you need is there with you.
Okay, can I ask a question? Okay, so typically, like these things, like you said originally, these guys are like a typical standard angle they just sit on. How much do you guys actually see this being utilized as far as being oriented and positioned at an angle? Have you looked at any changes that? is it really gonna gain that much to it?
Yes,
Element?
so we were citing sources specifically for finding like what the optimal tilts were. Like there are like winter settings, summer settings, and all these different things. And comparing it in optimal conditions, like in the summer, you could get up to like a maximum of a 60% increase in efficiency of power.
Please include, when you guys finish that, it'd be great if you guys actually incorporated costs associated with that, and payback time periods, because that would be phenomenal if that's really, we can see that, that could be implemented very easily, it'd be nice.
All right, one last one.
So, in the morning time, solar panels will be pretty much vertical when they're trying to catch the sun as effectively as possible. But what if it is really windy? Then those essentially vertical solar panels will act as sails, and they could possibly compromise the integrity of the stand itself. Have you taken any steps to take that into account?
When it comes down to the actual frame design, we have implemented worm drive systems and a planetary gear system. This resists any sort of wind flow, and we've calculated it should resist up to 40-mile-per-hour winds.
But
Anything higher than that.
And what about the frame itself?
What do you mean?
Meaning, if the solar panel is essentially acting as a sail, it could possibly bend the frame.
That's being taken into account with the frame design, with the integrity, planning on making it out of metal, like strong metals, thick metals, to ensure that type of stuff doesn't happen. And like certain situations, like if you have a permanent setting, you would obviously like get this deep in the ground, so that way it's not able to fall over in the wind.
Okay, your assumption is not mounted on the roof then, right?
For our current design right now, it's currently going to be like a ground mounted with a stand,
Okay.
just for our prototype's sake.
All right, last
Okay.
one.
Have you guys thought about spring loading it, so if it gets enough load on it, it'll just bend over?
Like a fail-safe system?
Yeah.
Yeah, that's take that into account.
All right, we can.